throughout the world, at least 60% of the water wells have failed and that were dug by hand when hand drilling in different parts of the world. But we have the different methods on the right-hand side in the yellow box and how they're designed to fail. Everyone knows that different types of drilling processes have a place where they fail, and each design of the drill is critical. Sledging's designed to fail when it hits gravel or hard clay or rock that is too big to enter the drill stem. And jetting is designed to fail when the depth is beyond the capacity of the jetting pump, and percussion is designed to fail when the cost becomes excessive, because percussion requires a lot of really heavy equipment. Think of a truck-mounted drill with a down-the-hole hammer, or a manual drill with a 400 to 1,500-pound weight on the end, and using it to break rock and drill a hole. So that's where those processes fail. With our drill, with the 1 million wells drill, we're able to bring up any size rock. I've brought up rocks drilling as large as 7 inches by 11 inches. So the advantage of our drill, of course, is low cost. The ability to drill where sledging and jetting won't work, and where percussion is trying to be used, but it cuts the rate of production, or increases the rate of production of the percussion drill. So in every formation, our drill will work, and all of the other drills have a design spot where they fail. You can go to the next slide. I can't see everything on that because your box is right in the way. Let me move it. Oh, it's not moving either. Okay. We have.
Press, there's a little miniature button to minimize the box. You can just press that little tiny level and it will reduce to a line.
Well, I hate to say it, but I don't have that. Okay, maybe at the end over here. Okay, that's better. But now I don't have the picture on.
But that's okay. We'll get to the people
I'm
soon.
sorry about this. I had no idea my computer wouldn't. Is your screen still up? Do you
it
see
is
a
still
large?
up.
Okay.
Right.
Well, this is minimized.
RC,
Yeah.
I can describe it to you.
Okay.
It's a picture of the guys in India drilling with the old drill with the pipe on it. It says where to drill, best way to drill, cost of drilling, building the drill, drilling the well, developing the well.
Jim, can you take it from here, because I can't see anything. It's just, I don't know what the problem is.
Well,
okay.
And ladies and gentlemen, I'm Jim Forbes, and I apologize for being late. I also had a little technical challenge getting it all open again, Mary, but here I am.
Glad you're here.
We train people worldwide, and we train them all exactly the same way. We teach them to use the Crawford drill, which of course was the Patent of Humanity Award winner in 2018. The drill is designed to perform best in alluvial plains. We can drill in other places, but it is not nearly as efficient and effective as it was. As an example, in Uganda right now, we're drilling in not so alluvial plain areas. The average drilling time is now around 3 days, and the average cost is about $500 to $600 more than what we're experiencing in India, including all salaries and compensation. Reverse flow circulation is a method that's been available for many, many years. It essentially removes all of the refuse from the borehole in the process of drilling. Unlike all other direct flow or down hammer or water pressure, which pushes the refuse in front of the drill bit. Particulates tend to move into the into the, for crying out loud, my brain is gone. move into the water stream or into the alluvial sands, and then at a later point in time come back and clog up the screen, which 47% of all the wells drilled in Africa today, as an example, are non-functioning within 12 months. In India, we drill 429 wells now over a 3-year period, and we don't have a single non-functioning well. Cost of drilling. Cost is tremendously less expensive than any other method, primarily because we're using only manpower, and the fact that RC designed the process to be built anywhere in the world with materials you could find anywhere in the world, with fabrication resources that you could find anywhere in the world, for as low a cost as it possibly could be done, because he recognized that most of the places where we'd be drilling, there was no money. Building a drill is a pretty simple process. We have a instructional manual for it, and we have a video for it, building the drill. Essentially, the drill is made out of a flat piece of steel, 1/4-inch piece of steel, cut with 4 prongs on it and welded to the side of a threaded coupling, metal coupling. There's a small hole drilled in the bottom of in the coupling. Air hose is attached to that hole, and air is injected into the bit. The drilling fluid goes down the outside of the drill stem instead of on the inside. The inside of the drill stem is essentially a closed air and water mixture. Blow a bubble in the bottom of the swimming pool, and what happens, it goes directly to the top. And the same thing happens inside of this contained space inside of the drill stem. And as a result of that, it provides a great deal of lift, and it extricates all of the material that the drill is grinding in the process of doing that. And we've moved cobble, gravel, and things as big as your fist from it. Anything that would fit in the diameter of the drill stem. After drilling the well, then of course the casing is put in. We make our own screen in most cases, although in India we have been able to buy screen that sufficed. In Africa, the screen that's available for purchase is way too big for this purpose. As a result of that, we have resorted to making our own screen. Developing the well. Developing as well is done with either air pressure or water pressure. Essentially, we're moving the water out of the casing back into the strata that's holding the water, stopping that and allowing it to purge itself until we've cleaned out the screen itself. Questions about that? Nope. Okay, good deal.
We invite questions in the chat, and what we'll do is continue on until the end of the discussion and have a open ideas period. So thanks. We'll continue with
will you advance? Thank you. We attended the United Nations Water Conference in this past spring. 1 Million Wells was the only charity to offer proof that they could drill, that we could drill enough wells to furnish water for about 2 billion people before 2030. There's a spreadsheet that RC will make available to you, or can make available to you, which proves that set of circumstances. The what we were disappointed about, I will go ahead and say, at the United Nations summit was there was a great deal of complaining and not much offer for problem resolution. In fact, we offered, to the best of my knowledge, the only problem resolution that was offered. And I said it in on multiple side events and the General Assembly. So we hope that USAID and other organizations like your own will come forward and say, hey, let's give this a try. Well, what we need right now is three things. We need awareness, we need partnerships, and we need funding. And with all three of those things, we can accomplish it. And 3 trips to Uganda now, counting my most recent one, we now have 5 groups drilling wells on their own. We are, however, having to fund the majority of those wells because there simply is no money, or if there is, we haven't been able to access it at this point in time. I had a sit down with the Ministry of Water in Uganda the first of this month. They basically are negative to involving it because they're negative to shallow wells because they basically don't understand what we're doing. And they admit in their own papers that they have over 5,000 non-functioning wells that they've paid to have drilled over the last 10 years. The drill, RC added to the drill the Crawford handle, a wire rope, pipe wrench, and the connections of the handle so that they could be moved up and down positionally within the drill set. The invention of the new tower method, including the use of the full depth steel percussion stem, came out of the work in Uganda. Essentially, when rock or volcanic tuft or other hard surface is encountered, we can drill through it, but it is a function of weight times velocity. And so we're having to either one, raise and drop the drill stem from additional height, and or use a different kind of bit, which we have several models of that can do a better job of penetrating.